Okay, so welcome to the colloquium today. So it's my pleasure to introduce the speaker today, Chip Rock. I only know him as Chip. I can't get Raymond across my lips. Is a special guest for us today. One of the people I worked with when I started my first postdoc. So that's quite a while ago. So Chip did his PhD at Carnegie Mellon, and then moved to Fermilab as a postdoc, worked on deep and elastic neutrino scattering, and after that took a faculty job at Michigan State University, where he is still today. And he's one of the original members of the D0 collaboration, one of the experiments at the Fermilab Tevatron. We have a second member with that honor in the room. Dave Cutts was also, I think, an original member of the D0 collaboration. I was maybe the 1,000, whatever. And I worked with Chip when I joined the D0 collaboration on measuring the W mass to, I don't know, a gnat's ass or something like that. That was a tricky enterprise. And after that, our paths split. Chip went on to Atlas, and I went on to CMS. But we're still friendly competitors, I guess. And well, Chip also has been department chair, and he's been chair of DPF in 2010. But most recently, he's been heading the effort that took place last year in 2013 in the so-called community summer study, where the whole field of high-energy physics came together to discuss and explore what the future might hold. And there were different groups formed that study different directions that the field can evolve into. One of them is the Energy Frontier Group, and together with Michael Peskin, Chip was the leader of that group. And so that's maybe the hat with which I've invited him today, because I hope he can convey to all of us what his view of the future of the energy frontier might be, and maybe also a little bit about how we arrived at that. So with that, thank you very much, and I'll hand the floor over.
Thank you, Uli. It's a great pleasure to be back at Brown. As you can tell, I was a teenager when I worked with Uli when he was a postdoc. I've collaborated with everybody in what is really one of the best high-energy physics groups in the country. It's most productive and has been for many years. And it's nice to be friends with all of them and have worked with all of them at one point or another. As Uli said, I'm going to try to describe to you some of the planning on the so-called high-energy frontier in particle physics as viewed by the United States. Of course, we don't do this by ourselves anymore. But I would like for you to come away with sort of three things in mind. The first is that you all know that the Standard Model has been confirmed. And the victory laps are over now, because we realize that the confirmation of the Standard Model is really the beginning of trying to unravel a number of curious things. And I'm going to spend some time trying to convince you that the Standard Model the completion of it really leads to new things. The second thing is I'm going to explain to you a little bit about this study that Uli alluded to, and I'll give you some of the results of the energy frontier decision-making that went on during that process. You know, it takes an entire city to plan in high-energy physics. It requires lots of us, because we're so project-oriented. We have to think 20, 30 years into the future, and that's a really hard thing to do, as you can imagine. And the process that we've typically used is, we call it the snowmass process, and there's a reason for that. It's a sometimes weird mix of community and agency, collaboration or not. The community studies have often in the past been sort of on their own, and then the organ in high-energy physics that stands between the community and the government sometimes does its own set of studies. This time, this was collaborative. The community study was meant to be the input to a long-range study, and from the beginning that was the case, and that's the first time I believe that's ever happened. So the community is indeed the Division of Particles and Fields in the APS, and those summer studies have typically been held in Snowmass, Colorado, hence the name. We'd all get together, 1,000 of us, for 3 weeks, and work together really hard for those 3 weeks, maybe hike a little, and then write up an enormous document that would hopefully make suggestions about how the future of the field should go. There have been lots of them. Sometimes they're focused, sometimes they're general. The last general meeting was in 2001, and about 2010 and 11, we began to realize it was time to really do it again, a general all-field discussion of the future of particle physics. And the time to do it was when people could pay the most attention to it, and that was not until the first LHC run ended, hence the summer of 2013. So that was targeted for quite a while. It turned out that because of the GSA scandal, the idea of 1,000 DOE and NSF-supported physicists going to Snowmass, Colorado for 3 weeks during any part of the year was completely out of the question, and we had to find a new way to do it, given the rather strange and difficult travel restrictions now that exist in the federal government. So we invented a new kind of Snowmass, one that was going to happen over the course of almost an entire year. We started in October of 2012. We worked for almost the entire year, and then about 1,000 of us got together in August last summer in Minneapolis. We kept the brand, and we called it Snowmass on the Mississippi. We have this theme that has a gift to us from the last time there was a long-range planning for particle physics. The frontier theme, the energy frontier, the cosmic frontier, and the intensity frontier. We've gone back and forth about whether we love or hate the idea of the 3 circles, but nonetheless, I think the thing that's clear is the 3 circles are here to stay, and so Snowmass was organized around them. Our sentiment typically, of course, is the intersection of the frontiers, but that sometimes gets lost. But for organizational purposes, we kept the theme, and we added some frontiers. We added a frontier of computing, instrumentation, facilities, and outreach. And then when the Beltway discovered we were using the word facilities, they got very unhappy, and we had to change that name to capabilities. My job, I missed a meeting somewhere in 2011, and I woke up and found myself co-convening the energy frontier with Michael Peskin, as Uli said. And so off we went to try to herd hundreds of LHC and ILC hopeful physicists in a direction that would lead to something coherent about what the physics prospects might be for future facilities. You know, in particle physics now, we absolutely view the future through the lens of the Higgs boson. The discovery of that very odd particle has shaped everything about how we think about the future, hence the title of my talk. So what I found myself doing was beginning to rethink in an entirely different way, think in an entirely different way about the future of the field than I had before. And so what I'm going to do today is sort of expose my perhaps neurotic picture of the field from 30,000 feet, a high-level view about why I think these are really exciting times for particle physics. Now, as everybody knows, especially those of us in Michigan, between 1967 and 2012, history was made. For the first time, a Triple Crown winner happened in all of those years, and of course, we expect that to happen again next year. But what you're probably thinking about in 2012 is the discovery that was announced on July 4th, 2012 at the CERN auditorium. Except for a few dignitaries in that room, everybody else there is a graduate student who slept outside the room overnight in order to get a seat. The rest of us watched it on computer, where the 2 experiments announced their discovery of a spin-zero particle at mass that was expected if the standard model were correct. The Director General stood up and said, we have a discovery. And so from that point on, the significance of those original sort of 5 standard deviation signals was established and got better and better. We published, of course, together, and not to lose track of this, but Fermilab also was at work looking for this same spin zero object in a final state that is difficult for the LHC, but more amenable to a PP bar collider. And 2 days before the LHC announcement, Fermilab announced evidence for, at sort of a 3 standard deviation level, a spin zero particle at just the same region of mass as at the LHC. So it was a remarkable pair of days after a long, long time of living inside of the same description of nature. That's really kind of unusual. And I like to try to explain why I think that's unusual. In any case, for my entire career and for the entire careers of many of us, we've all worked within this single description of nature called the Standard Model. It's a remarkable thing, and its tenacity is also remarkable over all that time. I think it's unusual historically in the 20th century for something to be so remarkably precise and accurate, and at the same time sort of live with mathematical unhappiness buried inside of it. So this historical time, I can only think of one other time, frankly, in the history of physics that's comparable. And so here's my particular neurosis. Let's think about electricity and magnetism for a second. When Maxwell wrote down his original theory around the time of the American Civil War, it made a decisive prediction that it took almost 2 decades to achieve, namely the electromagnetic waves. Not soon after that, Zeeman and Lorentz began to postulate about corpuscles of electric charge. The electron was, in fact, of course, discovered not long after that by Thomson, and then off went a theory, an effective theory of electromagnetism that influenced physics but also started industries. A very highly trusted description of nature. At the same time, it became very clear to people, especially after the discovery of the electron, that the electron indeed had difficulty. It would interact with its own field in ways that were difficult to control. And so during this entire period, there's this weird schizophrenia between a theory that is well trusted and undeniably a part of nature, mixed with this catastrophe of a self-energy crisis that nobody really knew how to handle. Dirac came along and suggested a way out that indeed was confirmed very quickly in experiment, and then the Lamb shift and Shelter Island occurred, and field theory was effectively born, relativistic field theory effectively born, and some of these problems began to be understood in a fundamental way. Okay, now the Standard Model. In the Standard Model, there was a group of people that had sort of the same idea at just about the same time, followed by Weinberg and Salam, who created a model making use of those good ideas. It made a prediction. A decade and a half later, the prediction comes true with the discovery of the W and the Z. In the middle 1980s, early 1980s, people began to think about phenomenology of the Higgs boson and what it might be. And then for the next couple of decades, the Standard Model continued to get better and better and better in terms of prediction compared with experiment. And it just seemed to be frustrating as heck that there was never any bend with the Standard Model. But and of course, culminating with the discovery of the Higgs boson, ultimately the final piece in that story. But simultaneously, the Standard Model was known to be sick. It has issues inside of it that are indeed in part a self-energy crisis. The same sort of schizophrenia existed. And so in my way of thinking about this, we're still working toward our Lamb shift Shelter Island moment when this is going to become more well understood. So I think these are strange and exciting times, not the end of anything. It's a new chapter, of course, in the study of the story of mass, which we began in a kind of a shaky way with the definition from Newton Before Lavoisier was separated from his head, the idea of a conservation of mass was enunciated. And then, of course, along came Einstein with a new way of dress that we all are aware of now, but also he linked forever the idea of mass and energy. Soon after Einstein, then came Paul Dirac, who now linked the vacuum with mass in a way that we no longer quite believe, but nonetheless, it was also Dirac who then sort of invented the notion of particles being created and annihilated out of the vacuum that eventually became the staple of field theory. And then came Gross, Politzer, and Wilczek, who sealed the deal with the gluon into a theory of QCD that made sense, and that meant that massive stuff began to be understood in an entirely different way, that the mass of stuff is not necessarily the sum of the masses of the material things that make up that stuff. That is to say, now we recognize that the proton itself weighs much, much more than the elementary constituents inside of the proton, and that the inertia of the proton indeed comes from the energy of the gluons, and we're back to using Einstein's equation the way he originally wrote it, namely that the inertia of the proton is due primarily to the field energy of the gluon. And then Weinberg, Salam, and Glasgow wrote down the thing that we now call the Standard Model, with really the Weinberg paper could still be read today in many ways. It's a 3-page paper that still kind of describes things in just almost the way we do them today. That's called the Standard Model. Well, what is it? Well, of course, there's a stamp collecting part of the Standard Model. That is to say, there are constituents that make up the Standard Model. The constituents are quarks and leptons. They're all fermions. They're arranged in patterns that are fundamental to the theory, and the group theory, and the separation of electric charge being one between the top and the bottom is apparent, and the family difference from left to right is primarily only mass. But it's not good enough to just collect the stamps. That's a fine hobby, but the idea is to understand the fundamental forces of nature, which is how the constituents talk to one another. And that comes through the spin 1 intermediate vector boson fields, which I like to call the messenger fields. The fields that carry the message of the weak interaction, the W and the Z, the field that carries the electromagnetic interaction, the photon, and the field that carries the strong interaction, the gluon. That's the Standard Model in sort of the standard picture. But the Standard Model contains ingredients that are really interesting the way they came together. They contain the ingredient of the gauge principle, which is a very pretty idea, and the ingredient associated with critical phenomena, namely spontaneous symmetry breaking. In fact, almost 2 different fields were involved in the origin of the gauge principle and the work that went on that led to an understanding of spontaneous symmetry breaking. The crucial marriage here was putting those 2 things together. And of course, today we could call that the Heisenberg, Nambu, Anderson, Schwinger, Brout, Engler, Guralnick, Hagen, Higgs, Kibble mechanism. And of course, it's called the Higgs mechanism. They're the gang of 6 who were assembled for the Panofsky Prize, except for Higgs. The interesting part of this history I'll come to in just a second. Let's talk about the gauge principle, because it's pretty. The gauge principle simply says that if you have a generator of a group with a charge and expose the particles in your theory, the fields in your theory, to a global parameter, which think of as an angle as the same angle for every field, then you just apply an operator to the constituents of that field. As an economy, that takes the entire space of fields that might be useful, and if you demand that your theory be invariant with respect to that transformation, it reduces the number of theories that would be acceptable. Okay, that's idea number 1. Idea number 2 is now make that parameter not the same angle everywhere, but at an angle that depends on space and time everywhere. Make it local. Now, that's a much more restrictive condition. Now, if you demand that your theory be invariant with respect to that particular local transformation, the kinds of theories that are acceptable are many, many fewer. Okay, from an economical point of view, that's nice, but what's really neat about the gauge principle is that this sort of invariance requires the existence of a spin 1 field. It not only does that, it provides for free the coupling of that new spin 1 field with the constituents of your theory. In many ways, it's a kind of a magic trick, but it's a pretty one. It says that the demand of a symmetry forces you to invent the photon. Now you've got an idea on how to build models. Start to look for symmetries. So spontaneous symmetry breaking, on the other hand, is a different good idea. Just like in a magnet above the Curie point, a magnet has a large symmetry, rotational symmetry, and the free energy has no minimum except when the magnetization is 0. You lower the temperature and the magnetization suddenly picks one of the 2 available spots in this particular model. And still, the Hamiltonian respects the original symmetry, hence spontaneous, sometimes called hidden symmetry. Now, what happens in this view of the world is that somewhere there's an experimenter that's actually changing the temperature. And there are actual theories that describe what goes on when that occurs. Keep that in mind. So now let's talk about this courtship and marriage of those 2 ideas. There's the particle theory path, as I think about it, and there's the critical phenomena path in condensed matter and many-body physics. In particle theory, I think it's fair to say that the gauge principle was a motivation, and in critical phenomena, I think it's fair to say that much of the ideas of spontaneous symmetry breaking were at work. The idea that you could invent the photon by demanding a particular symmetry, that U1 gauge symmetry, that was appealing, and it's a very old idea, actually, going back to Weyl. Well, the weak interactions are a funny kind of interaction. They're local, and so they require a massive spin 1 particle. So surely there's a gauge principle that would allow you to describe the W using such a symmetry idea, but that doesn't work because you always get a massless spin 1 boson whenever you apply the gauge principle. So that's sad. Then there are the ideas associated with a lot of people, Landau, Ginzburg, Nambaugh, Goldstone, in particular the so-called Goldstone theorem, suggested that in critical phenomena, you can't avoid the existence of a massless spin 0 particle. There were no massless spin 0 particles, so that was a problem. Notice that it's mass that is always the happy or sad part of this story. I think it's fair to say that Anderson came at this from a critical phenomenon point of view, and he found that if you combine together gauge symmetry with the ideas of, in particular, Goldstone, you could evade what appeared to be an airtight theorem associated with Goldstone, and in fact perhaps explain the Meissner effect as looking like a massive photon. At the same time, essentially the same time, all the people that I mentioned before had essentially the same idea, but in a more complex area, namely in a relativistic framework. Anderson's work was in a non-relativistic framework. These guys worked in a relativistic framework where manifest Lorentz invariance was an important part of the story. In the meantime, Glashow was working on unifying specifically the weak and electromagnetic interactions, and he required 2 spin 1 massless fields. Again, a problem, but a promising idea. And along came Weinberg and Salam with essentially the same idea, again, essentially the same time, that put all this stuff together to create a theory in which there was a distinct prediction of a massive spin 0 object, the Z, which had never been seen before, but sort of predicted by Glashow, except now with a mass, and of course accounting for the W. And in the end, that was a good idea. And it predicted the existence of a massive spin 0 particle. So that's what we think of now as the standard model. So what's great about it? Well, I think what's great about it so far has been the gauge principle. In a way, it's a way to explain how the W got its mass. It's the Standard Model. Was it Kelvin that said that in order to show that you understand a theory, you've got to be able to write it on a T-shirt? Maybe it wasn't quite like that, but it does fit on a T-shirt, and I know if you don't have one, you want one, right? You can all get a copy of the Standard Model, and let's go through what's on the Standard Model T-shirt. In pictures, I know you're not supposed to show a Lagrangian in a colloquium, but I'm going to make pictures out of the Lagrangian, so it's okay. The first couple of lines describe how the spin 1 objects of the Standard Model interact with one another. The second line describes how the spin 1 objects interact with all of the constituents that are spin 1/2. It's great because from those ingredients, decades of careers are spent in filling this table. I'll just tell you, you don't have to read the table. There's remarkable agreement to many decimal places between prediction of the Standard Model and measurement. It's the most accurate and most precise scientific model in the history of physics. The rest of the T-shirt is a little more problematic. That's where the Higgs boson comes in. The piece at the end describes how the Higgs boson interacts with spin 1/2 particles. And the important thing is that it couples to these particles proportional to their mass. The other terms in here describe how the Higgs boson interacts with itself, and the first term describes how the Higgs boson interacts with the W and the Z. Now, just like the little girl in the nursery rhyme, when the Standard Model is good, it's really good. But when the Standard Model is bad, it's very confusing. So what's embarrassing about the Standard Model? There's actually quite a bit. First of all, it's just a model. Everybody needs a hobby. Mine is orthopedic knee surgery. I could write down a theory of walking, a Standard Model theory of walking involving, blocks and arrows and Newton's laws, but that would not be a dynamical theory of walking. It wouldn't involve muscles, bone, nerves, blood, all the things that are required to really describe the physiology of walking. What I would describe with Newton's laws would be an effective theory of walking. That's what the Standard Model is. It's an effective theory. It's not a dynamical theory of anything, such as the BCS theory is a dynamical explanation of superconductivity, not an effective theory. What else is embarrassing about the Standard Model? Well, just about everything involving the Higgs boson. This thing is not your father's particle. A spin 0 particle with a mass has never been seen before. Now that's interesting. The nature of the Higgs particle itself is confusing. The Higgs boson story is confusing. It involves just a kind of a magical change of sign. There's no experimenter coming in and changing the temperature to make spontaneous symmetry breaking work. The theorist goes and changes a sign from plus to minus. So there are deep puzzles in this model that have been known for a long time. Theoretical puzzles, experimental puzzles, and even conceptual puzzles. So the Higgs particle itself is indeed strange. It has the quantum numbers of the vacuum. Right off the bat, that's a little odd. In particle physics, how many things are just one thing? Well, nothing is just one thing in particles. All of our things are members of families coupled together by symmetry groups. But the Higgs boson is sort of neither. It used to be a part of a doublet, but now the partner in the doublet is no longer there, and so now it's sort of a singlet. Let's call it a singleton, because it's not really a singlet and it's not really not a singlet. Is it alone? Is there really only just one Higgs boson? Well, maybe it too is a part of a family, in which case we've got to find the other parts of the family. Maybe it's different in tiny, tiny details from the one that we think we've found, and we have to look really, really hard in order to discover what the tiny details are about the Standard Model Higgs boson that we think we've found, and maybe the one that's actually there. And the Higgs, so-called Higgs mechanism is even stranger. Here are things that I think are strange about it. First of all, it's on all the time, the Higgs field. Second of all, the story is interesting but a little bit strange. The third thing is loops, and the fourth thing is doom. Everything about the Standard Model that I think is confusing is all balled up in the potential, the thing that I drew at the bottom of the T-shirt. The vacuum energy, well, that's best known as the worst prediction in the history of physics. The Higgs mass term here is distinctly described in the Standard Model. The coupling of the Higgs to itself carries within it the prospects for an unstable vacuum. That's not a good thing. And then, of course, the coupling of the Higgs boson to the fermions in the theory had better be the way the Higgs mechanism predicts it. Okay, always on. Well, back to the spontaneous symmetry breaking business. Once the symmetry is broken, just like in a magnet, the symmetry is reduced, and the symmetry is, for an infinite magnet, it's the same everywhere. It's in the ground state. The magnetization is always on. In the Standard Model, in the same way, where now this is the Higgs field, not a magnetization, the end result in the Standard Model is two different modes of degrees of freedom. One that circles around the bottom of this well, if this were coming out of the screen, and which disappears, by the way, in the theory, and the other climbs in and out of the well and becomes the excitations of the actual Higgs particle out of its field. But the point is that it's always on, everywhere. The story that we tell about the Higgs boson is a little bit strange. We think it's a story about how the electron and all those partners of the electron got mass, including the quarks, and that's the mixture of the gauge principle with spontaneous symmetry breaking. And the idea is that sometime in the universe it was really, really hot, the Higgs field didn't exist, everything's whizzing around at the speed of light, and then the universe cools. And when the universe cools, all of a sudden the Higgs field is now on, and these objects suddenly have gained mass because they see the Higgs field. So the masses of fermions in this story depend on the particle. A light particle seems to interact sort of less than a heavy particle because that coupling, remember, is proportional to mass. The masses themselves are an insult. In a scale in which we just declare the proton to have mass 1, the masses of the elementary particles are all over the place. It makes no sense whatsoever what the patterns are, except that in families they tend to get heavier and heavier. But the whole business is a big mystery, and while the coupling to the Higgs boson may be a part of the story, exactly what that coupling is a matter of measurement. It's not a matter of fundamental understanding. And then there's the whole issue of loops. This is where the theoretical community spends most of its time. In a relativistic field theory, the Feynman rules say that whenever you encounter a loop, and you must encounter loops, that you're obligated to integrate over the entire phase space within that loop. And you must do that for all of the particles in your theory that could be in that loop, and all the particles in your theory that may or may not be known. That is to say, it's a great way to search for new particles. And loops have been used for years in order to do precisely that. Now, your hope is that once you integrate from 0 to some cutoff, that you can deal with that cutoff in an acceptable fashion, and in the gauge theories, that's possible. But like I say, loops aren't mystical. They're a part of our language. We knew about where the top quark mass was because the Standard Model told us through those loops. The loop of a top quark and a bottom quark with a W on either side. So if the top quark mass, the Standard Model constraints coming from other ingredients involving the Standard Model pretty well tracked to where the top quark had to be. Likewise, what I used to call the Fermilab plot, but I can't anymore, is the plotting of the mass of the W boson versus the mass of the top. They're coupled, again, through loops. And in diagonal lines here, each line in the green would represent the standard model for a particular Higgs boson mass. More and more precision in the measurement of the W boson and the measure of the top quark would begin to slice out a region, and that had better agree with where the Higgs boson was. So we kind of knew where to look, and this is how we knew where to look, because of those loops. Okay, how about a spin zero elementary particle? Loops are problematic there. If you've taken field theory, you'll remember if you're renormalizing the mass of the electron, say, you'd have the mass of the electron in front, and the cutoff term would be in a ratio in a logarithm. For a spin zero object, the cutoff term is manifestly dimensionful. For some, this is an indication that cutoff sitting there actually represents a physical consequence. But if we just go through and follow the same rules from the previous slide that are well understood and calculate the corrections to the Higgs mass due to loops, there are these three loops that we know about. The Higgs boson loop, a top loop, and a W and Z loop. The thing about the Higgs boson that's complicated is its mass is light. It's only 125 times the mass of a proton. And so you've got to add up all these contributions, and you've got to get 125 squared on the left-hand side of that equation. So you can calculate, a graduate student can calculate what those mass corrections are. And they're huge for the top quark, indeed the other sign. So that requires that somehow this tree value that would be a product in the electron renormalization has to balance out this bad behavior by the top quark loop in order to have the physical mass be so small. This is called fine-tuning, and indeed it is an unfine tuning. If the next scale of physics, where lambda would be, was the Planck scale, that would require a subtraction of that many decimal places minus that many decimal places in order to get 125 squared. To most people, this is an absurdity. As Tom Hanks reminds us, there's no crying in baseball. Similarly, there's no such thing as coincidence in science. So, I think this is a hint, and a lot of people think this is a hint from nature. Now, we do know what to do about this. You just add in more stuff, right? You add in new kinds of particles that are designed to counteract that top quark business. And so new stuff at just the right kind of mass, at just the right scale, would naturally fix this problem. We know how to make such things that would do exactly that. And they're all sort of top-like things coming out of different kinds of models of physics. Supersymmetry, the so-called little Higgs, the composite Higgs. Indeed, a composite Higgs is a kind of an interesting idea because it's sort of like a Cooper pair in superconductivity. Absent this, people are beginning to talk about a variety of things that a lot of us would find sort of distasteful, especially an anthropomorphic notion. Anyway, 1 TeV is the scale, regardless of what the theory is. 1 TeV is the scale that's appropriate to balance out that bad behavior. Here it went again. Oh, I see what I did. I only do this 5 hours a week. Okay, then there's doom. This coupling in front of the self-Higgs couplings, this coupling varies with scale, just like the electromagnetic alpha varies with scale. And for the Higgs boson mass of about 125 GeV at scales that are not outrageous, that thing can actually change sign. Once it goes negative, then you've unbounded the vacuum. It becomes unstable. So, where's your weirdness scale before you would agree that maybe there's something missing in the standard model that we need to explain? All these ideas here are, to me, indicative of a hint. We also know of experimental hints that beyond the standard model physics. I think the Higgs boson mass being small, that for me is an experimental hint already. Neutrinos, just about anything involving neutrinos and their mass, that's been beyond the standard model physics since the first oscillation confirmation. Dark matter obviously needs a quantum. The fact we're here means that the universe is not equally mixed between matter and antimatter. That needs explanation. The G-2 results for Brookhaven need confirmation and disconfirmation, and that donut has traveled all the way around Florida and up the Mississippi River to Fermilab in order to check those results. But these two are strong hints that beyond the standard model physics exists. Okay, so now back to SNOMAS. G-2, the new one, that's right. Part, there's a sort of a 3.5 sigma deviation from electromagnetic corrections, even the additional corrections that might be indicative of seeing supersymmetry. No, that's right. Just the muon. I think because the scales cause new physics to come quicker for the heavier particle. So our study started, like I said, in October. It ended in August. The Energy Frontier group that Michael and I herded had 21 meetings in that time frame around the country. The end result is a book that's just about to be published. It was given officially to HEPAP, which is the High Energy Physics Advisory Panel, standing between the community and the government. And immediately a new P5 was commissioned that's sitting right now to try to figure out what the best thing is for the future of particle physics in the United States. We restricted ourselves to not picking winners and losers. We did not make recommendations in the community study that said we should go do ILC and stop the phase 2 upgrades. We didn't do that. We evaluated the physics opportunities at each of 7 different kinds of future accelerators and left it at that by enumerating those opportunities. Of course, there's a huge paper trail just from the Higgs part of the Energy Frontier groups, of which there were 6. There are lots and lots of white papers, and there are white papers for each of the other groups. And then that's just for the Energy Frontier. Each of the other frontiers similarly had a paper trail like this. So then the conveners spent weeks and weeks and weeks and weeks writing a single document to describe all of the frontiers. That was exciting. You can find them all on the web. And then we spent weeks and weeks and weeks and weeks trying to come up with an executive summary that we limited to 7 pages. That's a pretty long executive summary, but it would have been weeks and weeks and weeks and weeks more if we'd continued. Then we spent weeks and weeks and weeks and weeks coming up with a 1-page, 3-fold handout that could be used. And we've lived in dread ever since that the chair of the DPF, John Rosner, was going to insist that we come out with an executive tweet. One thing we did try to do was enumerate what we think are the important questions for particle physics. And they're questions that you'll recognize from the beginning of my talk. The Higgs boson, how do we understand the multiplicity of quarks and leptons, neutrinos, the antimatter matter problem, all this stuff. So for the Energy Frontier by itself, in fact, it tackles most of those important questions. So we had our hands full. So the lineup that we looked at were 2 different iterations of proton-proton colliders. The so-called phase 1 upgrade associated with the LHC, which at the time we chose with advice from Atlas and CMS to be 300 inverse femtobarns at 14 TeV. The phase 2 upgrade would be a factor of 10 more than that. We didn't consider explicitly the run that's just starting, which will be the first run at 14 TeV or 13, the design luminosity, and it will be about 150 inverse femtobarns of running, which is about 4 times, a little bit more than 4 times what we took in the first run. And then a whole collection of lepton colliders, E plus E minus linear, even E plus E minus circular, and a photon collider. And people worked on what they wanted to work on and voted with their feet. These are the working groups. The Higgs boson group, the precision electroweak group, the top quark group, the new physics group that Mina was an important part of. She saved our bacon by combining with a postdoc from Fermilab to create the simulation framework that everybody used. So results I'm going to show you, in fact, all came from a simulation designed specifically for SNOMAS, the quantum chromodynamics group, and the flavor and CP violation group. In addition, Uli stood between the Energy Frontier Physics group and the instrumentation group, thereby conveying the physics needs and then rationalizing that with the technical challenges. Our goals were to generate scientific cases that would motivate the two next runs at the LHC, the two high luminosity runs they're called. Is there a scientific necessity for precision Higgs boson program, we asked, and is there a scientific case for experiments at higher energies beyond 2030 when the LHC will be done with its current challenges? So here are our conclusions. Our first conclusion is we've got to measure the properties of the Higgs boson. We have to measure the properties very precisely of the top, the W, and the Z. Being the heaviest objects, they talk to the Higgs field the most, the strongest. And finally, we have to search for TeV scale particles just for this fine-tuning reason. So let me give you just a real short skim of some of the important results. There were many results, and I couldn't possibly go over them even to a energy physics audience. The Higgs boson. We know exactly what the statement of work is for a standard model Higgs boson. Any measurement that does not conform to that list is not standard model and would be indicative of beyond standard model physics. I got to show you Higgs boson production, and here's the same kind of event in both ATLAS and CMS, where the protons collide. It's really a gluon collider at LHC. Produce a Higgs boson that decays into two Z's, like the first term in the last line of the T-shirt, and then those two Z's have each decayed into electrons and muons, and there are perfect events of exactly that kind right at the mass of 122, 123, 124 region. This is the golden mode, it's called, of Higgs production. So how do we do this? Well, the coupling is the key to the industry that has now been established worldwide, an industry of theory and experiment both. The couplings, the standard model couplings that I've represented as little g, are now parameterized in terms of a constant factor, a kappa. And for each of the fermions, there's a kappa. And so the goal is a big global fitting with the constraints that are necessary in order to determine the kappas. Then the Higgs group went to models, and they picked a handful of models, all evaluated them at 1 TeV, and then asked themselves the question, how big would kappa have to be in order to be evidence for one or more of these models? How well do you need to measure kappas? And the answer is that somewhere between 1% to sub% would be sufficient to begin to rule out the standard model and maybe rule in new physics by finding some kappa that differed from the standard model at that level. So that sets the benchmark. And then the Higgs group then proceeded to evaluate what the kappas would be. Here's the kappa Z. And in here I've drawn the range that's 0.5% to 5%, sort of the interesting range for each of the 7 different kinds of future accelerators that we considered. You'll see that in some cases the ILC wins big, and in some cases the LHC does just fine, and in some cases, in fact, the LHC does a little bit better. So these were then tabulated, and I'm not going to bore you with all the numbers. The point is that the LHC is the beginning of precision Higgs physics, and depending on how far we need to go in order to find new physics, the LHC could very well tell the story. The masses kind of line up about where you'd expect them, and so we would like to say that the precision Higgs boson program has now begun at the LHC. Current precision is in the tens of percent. And then there's the electroweak group. The electroweak group worried about the physics of the W and the Z. And I'm back to the loops. The Fermilab plot again. This is from 2009, the same plot I showed you before of the mass of the W measured versus the mass of the top quark measured, and then the lines indicate different standard model results for that correlation as a function of Higgs boson mass. That's in 2009. Now it's 2014, but this was made in 2013. Now the band of green is gone because we know the value of the Higgs mass. Now it's this little tiny line. And by gosh, the mass of the W measured versus the mass of the top quark measured had better cross that line because that's where the standard model Higgs is. The gray circle is where we are now. The blue and the red circles are where we think we can go at the LHC and where we could go at an ILC, a linear collider of electrons and positrons. And so the electroweak group worked hard to figure out what were the systematic uncertainties in the way of doing a very precise measurement of the W mass, and they concluded that a 5 MeV over c squared precision on the W mass, which is 80 GeV, is doable. And so this is how well this could conceivably be measured. Then there's the top quark group. Oh, by the way, I should have mentioned, all this green area in here, this is a space of supersymmetry. So were this band to really continue to, as it always has, kind of lie at a lowish value for the Higgs and now really right on the edge, were that to continue to shrink and be off that line, that's got to be brand new physics. That's not standard model physics. In this case, the measurement of the W and the measurement of the top quarks are beyond the standard model searches from this point on. They're no longer confirmation of the standard model. Now the top quark group. Why measure the top quark mass any more precisely than it already is measured? Well, one reason is to keep up with the W mass. That correlation between MW and NT, you want to continue to also shrink the top quark mass. It's also a fundamental parameter. As the heaviest fermion, it's got the biggest coupling to the Higgs. And there's this argument about stability of the vacuum. That term, the scale dependence of that term depends on the mass of the top quark and, in fact, alpha strong. And right now, if you were to plot the mass of the top quark versus the mass of the Higgs, there's this region where the vacuum would be stable, and there are a region where the vacuum would be unstable, and there's a region in the middle where it would be metastable. And right now, the masses have come in at a very odd place, where it's just sort of metastable-ish, but still within, statistics and maybe systematics, headed toward the stable region. But for some people, this is big news, and for other people, this is sort of ho-hum. But nonetheless, let me at least say that perhaps it's another one of those hints. The top group also looked at searching for top partners for various kinds of theories, and they worried a lot about pileup. When the LHC protons collide, there's a lot of stuff that goes on there besides the collision that you want. In some cases, 50 or even 140 pileup events in the very high luminosity running. The LHC limits settable at the phase 1 running would go out beyond the 1 TeV level to about 1200 GeV for a top-like partner, which is code for something that would balance out that great big negative top quark loop problem. The new particles group, well, they're very much motivated by fine-tuning and dark matter. And they worked on a lot of different models, telling stories, indeed. They wrote, what, 28 stories? I mean, I can't remember, 21? Stories of discovery, what it would look like, what it would mean. That was a great way to go about doing that. You don't need to see this in any detail. This is the standard plot. Each one of these lines here is beyond the standard model theory. Each one of these bands is the degree to which one can reject at 95% confidence those new theories. No new physics has yet shown up at 8 TeV at the LHC. But when we raise the energy, the cross-sections are going to go up a whole lot, and then we're going to begin to start to probe in, for example, this is supersymmetry, the supersymmetric production of a stop, which is one of those hypothetical top partners that would balance out that negative blue. We could begin to probe it at ranges that are far beyond what you would think would be actually natural for a stop. It's possible that, and there are plenty of theories that describe a brand new intermediate vector boson, a new messenger particle. The Z prime is the one that's talked about a lot, but it's also a W prime. Electrons and muons would nail that. And this is work that a postdoc and I did for SNOMAS using Mina's detector we simulated and then animated the production of the growth of a Z prime at 3 TeV for up to the phase 1 luminosity for electrons and for muons. And the thing about this that's neat is not that you get to see this bump, but that would be neat at 300 inverse femtobarns. The thing that's neat about this is even halfway through the run that starts in January in electrons and muons, we could begin to see hints. If we saw such pimples starting to form in both electrons and muons in the next run, that's going to be a discovery. After 100 inverse femtobarns, it would be distinct. Having them both would be really neat. So this is a measurement that's going to be on the top of everybody's list when the run starts. In addition, then, the group asked itself, how high will the sensitivity to masses of a new Z be? And the masses will go out to something like 3 times what's been done up until this point. Then there's dark matter. This is a plot actually I stole out of the Cosmic Frontier group that was an attempt to try to put on one slide all of the existing exclusions and discoveries of the dark matter community. On top of that was a kind of a large region where supersymmetry might be active as a possible source of a dark matter particle, and particular models shown on there. Many of the cryogenic experiments all have this low threshold issue below about 10 GeV squared. And these are the projected limits from experiments that are not yet built. The LHC can do this in a variety of ways, and the limits that the LHC would make would be something like that. And the point here is not that it stretches out there where it's already ruled out. The point is that it also reaches down lower where the cryogenic experiments might have difficulty. In any case, the conclusion of the new physics group is that the TeV scale is indeed in hand for all of the kinds of facilities that we considered for many different kinds of models that we're going to nail the 1 TeV scale. Okay, the cases for future programs. For all of these programs, we wrote down the cases, the physics cases for each one of them. Here, for example, is the phase 1 upgrade physics case. The most important 3 were the clarification of the Higgs couplings, like I talked about, at sort of the 10% level. Theoretically and experimentally determined the top quark mass to 600 MeV, which is in line with the W mass precision that's required, and a ×2 sensitivity to new particles, Z prime, supersymmetry, all that stuff that I've been talking about. And then in addition, there are a whole bunch of other color-coded to the physics group justifications for that kind of experiment. The rest of them, we did them for all of them, and they're in the back of the slides if anybody wants to see them. Okay, let me mention 2 things and then I'll conclude. Thing 1 is about mass. We collider types like to say that we've discovered how mass is generated. Well, that's not quite the case. As long as we don't know anything about the neutral fermions, mass, namely neutrinos, and as long as we don't know anything about much of the gravitating universe, we really don't know the whole mass story. This is a serious problem. If the light neutrino couples like a Dirac particle, it's almost certainly a beyond the standard model process. Otherwise, that insult of the mass scales gets even worse. If it's Dirac, its tiny, tiny mass coupling really only makes sense if there's an expanded Higgs sector, because it's just too big a dynamic range. If it's a Majorana neutrino, then it has to talk to a different Higgs, and we've got to find it. So the Higgs sector in neutrino physics is an important part of that program. Do neutrinos get masses differently maybe because it's tiny? Then, wow, that's completely bizarre. The point here is that understanding mass is all hands on deck in particle physics for the next 20 years. It's not limited to the energy frontier. It's going to involve all the frontiers. The second thing is about those circles. You know, the bumper sticker frontier. Sure, they're pithy. We don't like them because of the way the Department of Energy has used them in funding people, and so they begin to compete one community against another. But I began to ask myself about the circles. And I'm beginning to rethink the metaphor. Nobody had more fun making fun of the circles than I did over the last year, but I'm actually beginning to change my mind. First of all, they're with us. We're not going to get rid of the circles. But somewhere, new physics is going to bulge. And where it's going to bulge, of course, we don't know. But it's most likely going to bulge in ways that it's going to influence the physics of the frontiers of cosmic and intensity. Can we make the frontier metaphor work better for us? I hope we can. We're all about frontier, of course, in the United States. Here's my romantic view of the frontiers. What was Columbus's standard model? Well, that he was going to find the Far East. He got a surprise just over the horizon. Well, here are 3 frontiers headed toward a horizon, the consequences of which we no longer have the kind of roadmap that we've enjoyed up until now. Up until now, for 40 years, you proposed an experiment to do what? You proposed an experiment to find physics beyond the standard model, and if that didn't work out, you confirmed the standard model even more precisely. You couldn't lose. You knew your experiment was going to be successful before you started it. Well, now confirming the standard model is no longer on the table, and that's the punchline. The Higgs particle changes everything. That's my point. The Higgs particle has caused us now to start to look at our future in a different way. We'll propose experiments differently. We'll assess risk differently. Because confirming the standard model is no longer on the mass shelf for us. It's no longer a goal. Instead, we're exploring. And it's the first time in my lifetime where we're doing particle physics without a known path, following the standard model, knowing exactly what we're going to find, just maybe more precisely, or we're going to know exactly what the deviation might be. We couldn't lose. Now it's different. We're exploring, and what's better is a definition of a frontier than exploration into places unknown. Thanks very much. There are logarithmic corrections, yeah. Well, I think they're pretty accurate, but I think that it's the one loop ones that dominate the whole argument. The logarithmic corrections don't fix it. Did I convince you?